Alrighty. I'm Kirk Haines, and I'm here to talk to you all about Vertebra. Now, just a little bit about myself. I've been doing Ruby for about 7 years and have been making a living off of Ruby for pretty much the whole time I've been doing it. For most of that time, I did web stuff. I did a lot of websites for businesses, for a lot of mutual fund things, using Iowa, which a couple of you may have used. And I also wrote Swift Apply and Analogger, which are two tools for making your stuff faster. And over the last half year or so, I've been working for EngineYard on Vertebra. Now, cloud computing, we hear a lot about it these days. If you follow the right people on Twitter, there's constantly things about cloud computing, how it's going to bring down costs, etc. And every day there are more and more people moving towards cloud computing for their deployments. EngineYard is obviously really committed to the whole cloud concept. And one of the great things about clouds is that they're made up of lots of relatively inexpensive computational units, little machines. And so it provides a huge array of resources for your software to do its thing. Now, that's also one of the bad things about clouds, is because you have all these machines, and how do you manage them? How do you distribute work to them? How do you deal with that? And that's one of the ways that has been done in the past, and it's a pretty common way to do it, is scripted SSH use. You have something that goes out and iteratively fires off its stuff to all your different machines. And it works, but for some things it doesn't work so well, and when you start getting large numbers of machines, it can get bogged down. And so that's kind of where Vertebra comes in. Vertebra is designed to be a framework for fault-tolerant services that are running inside your cloud infrastructure. Now, Vertebra is comprised. Did I unplug myself? There we go. Okay. Vertebra is comprised of a few different layers. Now, at the bottom layer, you've got the Vertebra Protocol. And that protocol is built on top of XMPP. And there's a whole bunch of design reasons why XMPP was chosen as the protocol. You can read through these, and that URL at the bottom points to a more complete document that explains all the design reasons. But what it all boils down to is that XMPP has been around for quite a while. It's a solid, mature specification and had a bunch of features that were useful. And so the decision was made to build this thing on top of XMPP. And XMPP, it's kind of ugly. This is an actual capture of one full exchange for one operation that occurred between two agents running inside Vertebra. And so you can see there's a lot of back and forth there of a lot of data. It's a very chatty protocol. Now, one of the upsides of that chatty protocol is that it gives a lot of information there for us to build fault tolerance in, because of that back and forth nature. If we go back to that protocol for a second, if you can see that, we're using IQ packets. And in the XMPP specification, a IQ set, which gets sent out somewhere, has to have a result that comes back. There's a handshake that occurs. And so we can use that handshake along with a couple other features where we retry packets that if we don't get a response in enough time, we retry them, and where we suppress, if we keep track of the packets we get, if we get duplicates, we suppress those suckers. And if we do that, and then what we have is we have a really fault-tolerant system. And the goal of that system is so that if you have two agents out there running, network drops off in between them. And while there's an operation going on between those two agents, when that network comes back up, that operation should be able to just pick up from right where it left off and complete without any intervention, any issues. That's what we're aiming for with this thing. Now, sitting underneath all of this, you have to have an XMPP server. And the one that we chose for that is eJabberD. And again, there are several reasons, technical reasons for that, and I gave you a URL where you can go and read what those are. But what it boils down to is that eJabberD is fairly fast, it is solid, it's been around a long time. I think, if I remember right, its antecedents were 1999, something like that. And using Erlang, it's actually extensible. So later on, if we wanted to, we could take portions of Vertebra and move them right back into the XMPP server. Now, the next section of Vertebra is the agents. An agent is nothing more than a process that's running out on some machine somewhere that encapsulates a set of resources that it's making available to the network. And so, for example, you might have an agent that handles all of your gem operations. And so it's going to offer operations for listing your gems, for installing them, for deleting them, whatever. You might have an agent that handles logging. So you can write a log, and it will go and store it someplace for you. And if you want to query logs, it can query them for you. And these agents sit there out on all your machines in your cloud, however many you've got, just waiting to do something. Now, once you have all those agents out there, though, you need a way to talk to them. You need a way to tell them what you want. And so what you add is you add another item that I've called a client agent. And a client agent's really no different than any of these other agents, except that its purpose is to act as a communications conduit for you. Now, that client agent, if you're going to use one of those client agents and you want to, for instance, run an operation to query your logs that have been written, that client agent needs to have a way to know which of those agents out in the cloud are valid recipients for that operation. And so we add in one other piece here, and this piece is called Herald. Now, Herald was originally written in Ruby, but the decision was made to rewrite it in Erlang for performance and scalability. And Herald it's just like any other agent out there, but it has a few important jobs that are central to the way Vertebra works. First of those is advertising. When an agent starts up, and one thing that I in my spiel I forgot to mention back there just a few minutes ago, is that all of those agents sitting out there, all those processes, those are all Ruby processes. In Vertebra right now, our agent infrastructure is all written in Ruby. And so every one of those is a Ruby process out there. Now, when one of those things starts up, the agent looks at all of the actors, which are, you can think of them as classes of functionality. It looks at all of the actors that it has defined for it to run, and it gathers up all the resources that those things offer, and it advertises them to Herald. And this is a capture of the operations that take place there. And what it does is it sends a packet over to Herald saying that we're going to advertise this list of resources. Herald takes that information and sticks it in an amnesia database where it's running, and then it just sends a response back that's essentially an acknowledgement that, that it has received this information. So coming back to our client agent there, that's all fine and great. We have all these agents out there that have advertised what they're doing, but there still needs to be a way to get that information back, to query it. And that's the second part of Herald's job. Herald offers discovery. And so what a client agent will do, and I see I stuck the wrong image in there, but what a client agent will do is it will send a discover off to Herald, and Herald will, and it'll say, I want to discover everybody that offers list letters, that operation. Herald will go look in its database for all of the agents that have previously advertised that this is what they do. And then it sends a response back. And it can be, like in this example, there's just one item in that list. Or there could be 100 agents out there that do it. It doesn't matter. Herald will send back whatever there is to the client agent. Now, when that happens then, the client agent can go ahead and can fire that operation off to those server agents out there and get the ball rolling on things. Now, a problem comes in, though, because you don't want anybody able to fire any operation off that any of your agents have defined. That's what happens when some bozo gets in there and starts installing malicious gems or something worse. So Herald has a third duty, and that's authorization. And so what Herald does is Herald offers a security authorized operation. And when one of those client agents dispatches an operation out to a server agent, the server agent looks at who that was that dispatched that operation, and it goes off to Herald, and it does a security authorized operation, and it asks, let me go back there. It asks Herald, is this guy allowed to do this operation? And Herald sends back either an acknowledgement or a disacknowledgement of that. And then depending upon that response, the server agent can either drop the communications or can go on with it. Now, back to my original example there of the log query operation. If you're querying logs, you probably don't want a whole bunch of servers and a whole bunch of agents all spitting back the same information to you from your query. You probably only want one of those guys out there in your network to do it, and you want to leave the other ones alone. And so there's one more component that goes into dispatching operations with Vertebra that plays into that, and that's called scope. And right now we've defined two scopes. One of them is a scope of all, and all, just like its name suggests, sends to every single one of the agents out there and collects all of those responses back and delivers them to you. And then the other scope is a single scope. And single scope just sends out to a single one of those agents at random. And if that agent blows up, if it returns an exception, something of that nature, then the system will pick another one at random, send the query out, and we'll keep doing that until it either gets a response back from somebody or it exhausts its list. And those aren't the only scopes that can be defined. We could define a lot more. There are several in the works, but that's what we've got right now. And roll all this together, and that's Vertebra in a nutshell. It's just a way of running processes out there, getting stuff out to them, getting it back in a relatively efficient, fault-tolerant way. Now, while we were developing this, we ran into some there are a number of interesting things that have come out of it. One of them is this thing is built on XMPP. And if you go back 6 months, a year ago, the main library out there to do this in Ruby was XMPP4R. And it works fine. But it's kind of slow. It's really heavy on the memory use. And it's threaded. Slow's relative. And you can make arguments either way, but in general you want things to go as fast as you can. Memory use is a big consideration though, because if you have, say you have 1,000 of these running out there in your cloud, and each one is using 10 megabytes more than it needs to, that comes into some real costs. And then the threaded issue is mostly because if all of the internal operations are happening inside threads, it makes it really difficult to get in there and finally control what's happening when, and whether it just makes it difficult to manipulate the internals. And so we started looking for something else to use. Now, Aman, and he's out here somewhere, he wrote XMPP4EM. And what he did is he took XMPP4R and he ripped out the threaded portions and made it evented using Event Machine. And it did offer better performance, but it didn't really help so much with the memory use. And so we kept looking around, and we came across this thing called Loudmouth. Now, Loudmouth is a C library, and it's written using glib. And it's event-based. It uses glib's event loop. It's pretty fast, it's pretty lightweight on the memory, and it has Ruby bindings. It looked like, the answer, so we went with it. And the end result was a faster product with the RAM use dramatically reduced. I saw agents with footprints of 20 to 30 megabytes with XMPP4R, and with Loudmouth we're at 10 megabytes. And in the intervening months since then, the original owners of Loudmouth, which is a Swedish firm by the name of Emendio, Michael Hallendahl is the main author, they have left the project, and so we've picked it up, and we are carrying it forward. So we had Loudmouth, and we're taking Vertebra, which was originally written with XMPP4R and threaded, and we're trying to turn it into an evented system. And we needed a way to schedule the work that would happen in these, since it's an evented system, things have to happen fairly asynchronously and without a lot of blocking. And so, for an example there, I have schedule an op to be sent, but don't send it unless the eJabberD connection is live and authenticated. That's one use case we needed. We needed some way to encapsulate bodies of work. Now, Event Machine, I mentioned it earlier, it has a implementation of the deferrable pattern in it. And this is actually a quote from the documentation there. The deferrable pattern allows you to specify any number of Ruby code blocks that will be executed at some future time when the status of the deferrable object changes. Now that's close to what we needed. It's in the ballpark. And this is actually, don't worry too much about the details of the code there. I know it's kind of small, but I threw that in just so you can see that the whole implementation of a deferrable is actually pretty small. And this is the event machine deferrable with all of the comments stripped out. Now, so remember that Loudmouth uses glib, which has a separate event loop. It has its own event reactor in it. And so I took the Vertebra, or the event machine deferrable, and I changed it to a Vertebra deferrable with just a few minor changes. First of all, the event machine deferrable, if there was a problem when you defined your callbacks or your error backs there, it wouldn't give you any feedback. And so I changed it so that instead it'll throw a custom exception if there's an issue there. And the next issue was that when you set the deferred status on a deferrable, and that status can either be succeeded, defer, or failed, the event machine one doesn't return the result of the blocks that get called, and I made my version so that it does pass that information back, because sometimes you want to know without having to use some other value passing mechanism. You just want the value from those blocks to fall right back out. So I applied that change, and then I also applied the change there to just make it work with the internals of glib instead of event machine. And crap, I put in the wrong slide there. I showed you the internals of event machine. But you get the point. And it was almost good enough. Almost good enough. Now there's only one issue. When you have some body of work that's scheduled, there's some conditions that need to be met before that body of work runs. The example I used earlier is we want to make sure that the eJabberD server is connected to and authenticated before we dispatch that work. And so we took that deferrable, and I made another class out of it that I called Synapse. Probably should have been called Neuron, but and all a Synapse does is it provides another set of blocks that are called conditions. And those blocks can do anything you want. And what they need to do is, at the end, they either return a true or a false, or they can return symbols, succeeded, deferred, or failed. And a true is equal to a succeeded. And so what happens is when that block of code runs, if it returns true or succeeded, then that condition has been met. If it returns deferred, then that condition didn't fail. It just hasn't been met yet. So we'll come back and revisit it at a later time. And if it returns failed, then something went wrong, and we need to call the error condition, the error callbacks, instead of the success callbacks on a deferrable. With that added in, it was the perfect thing for controlling our blocks of work. And this is a little snippet of code showing how it's used. This actually comes from the client protocol. When we start a connection, or not a connection, but when we start a transaction with a server, the first thing we want to do is make sure that our connection is open and authenticated, and make sure that we don't already have a conversation in process with that particular JID. And then if those two conditions are met, then we fire off the callback. And it's as simple as that. It makes it really simple to define future units of work that may or may not get executed depending upon a set of conditions. And by using the same thing, it also makes it possible within the agent framework to encapsulate long-running operations. Let's say you have a backup that you want to be able to initiate with one of your agents. Backups can take a long time, and you don't want that long-running process to be blocking either your agent or to be blocking whatever is talking to it on the other end. And so we can use the same thing, the same with just a little bit more sugar in there to make it really easy to wrap up long-running processes. And so an actor synapse just supplies a little bit of sugar there. It provides a default condition to evaluate what's happening with that long-running condition, whether it has completed and there's results to pass on, or whether it's still running. And what I have here is just sort of a contrived example of a long-running operation. All it does is generate a string of some length, but it does it over a period of seconds. And when this runs, it doesn't block the reactor while it's running, because it breaks each of those into a little bit of processing inside a synapse, schedules them on the reactor queue, and it just churns through it as it's ready. Now, that's just kind of the start of the concurrency API. There's other ways that we're going to go with this to make it more friendly to our users. We might do something with fibers. We might do something with automatically managed for processes. It's kind of the future, but that's kind of the start. Now, coming back to Loudmouth there was one pain in the butt with it. Loudmouth used glib, and glib uses Ruby GNOME, and Ruby GNOME is a really heavy dependency. It's kind of a pain in the butt to build on OS X machines. And then the other problem there is that because it has its own event loop, that doesn't play well with an event loop like out of event machines, both of them trying to run in the same Ruby process. You can do it by interleaving the two using timers, but it's ugh. It's really nasty. So there had to be a better way. Now, there's an outside contributor, Raphael Simon, who works for RightScale. And RightScale uses EM for a lot of their stuff. And he has been looking at Vertebra for some stuff that they're looking at doing internally. And so he needed to interface this, and he thought there had to be a better way. And he made one. His requirements were that the glib event loop shouldn't ever be blocked, so that traffic coming into Loudmouth, XMPP traffic, is never held up while Ruby is off doing its thing. And it also should be possible for you to take some long-running process in Ruby and easily spawn it out without blocking anything as well. And so the solution he came up with is to take glib, because it's a self-contained C system, and run it in a separate thread from Ruby, but to manage that from the Ruby bindings. And then inside the Ruby bindings themselves, he's using Event Machine to control all of the communications. And so his answer to doing that was to use pipes to communicate between the glib thread and the Ruby thread. And what we have here is, if this is sort of the flow of how things go when you're going from Ruby to Loudmouth. Ruby needs to talk to Loudmouth, so it writes something into a pipe that's going into Loudmouth. Now, Loudmouth's event loop picks that up, and that activity on that pipe, and it knows that when that happens, it needs to pause its own activities and then go tell Ruby to pass the information back to it as to what it needs. And then it resumes its loop and it runs it. It's a pretty elegant system. And then the same thing works in the other direction. When Loudmouth needs to talk to Ruby, it does a very similar sort of thing. It pushes that information out to Ruby. Ruby picks it up, signals back to Loudmouth that it got it, and then Loudmouth can go on with what it's doing. So there's two threads that are running concurrently, but because Loudmouth is self-contained C, it's not Ruby itself, there's no issues with this compatibility with 1.8.6. It works fine with 1.8.6, and it should work fine with 1.9 as well. I haven't tried it there yet, but it should work fine. And this was really nice because it eliminated that Ruby gnome dependency. It did add an event machine dependency, but that's a lot lighter weight dependency, and the old model is still available in those Ruby Loudmouth bindings. It's still pretty fast. The RAM usage is still low. It does add about a megabyte to the footprint, but it's still pretty low, and it lets the agent code use event machine for whatever else it needs to use without blocking anything. So it really worked out nicely. And then putting all that back together, coming back to that whole concurrency issue, now that Vertebra employs Event Machine internally, and Event Machine has some nice facilities for spawning processes out and interfacing with them in an evented way. You can do things that take a little bit of time, and you don't block anything in the process. And this is an example of an action that does just that. Now, what it does is it spawns a DU operation out on the disk, and while that spins, the reactor goes back about its business, and then periodically this little block, this little bit action is checked just to see if that external process has closed or not. If it hasn't closed, it goes back to sleep for a while and comes back to check it again. And when it has finally closed, the data is returned. And actually, if I can show you a quick, go into the realm of a live demo here. I'll show you a quick, this is just a simple operation. If I didn't kill my stuff before I started my talk, and maybe I killed it and closed the wrong shell. Okay, maybe I shouldn't have gone to live code. I killed my demo before I started my talk. So, yeah. Any questions? I have no idea how long I just took because I forgot to turn on Mike's little timer here.
I got one.
You were in the lights. I couldn't see you there.
Who's using Vertebra right now?
Right now, we are starting to work on using it internally at Engine Yard. We're working on some stuff to do DNS provisioning with it. And RightScale, as I mentioned, has been putting quite a few resources into it at their end to explore using it for something that I don't know what. And so far, that's all that I know about that's really using it. We've had interest from some other groups, but.
Where do you see the relationship between things like Vertebra and the nanite stuff?
Vertebra and nanite are conceptually similar. I personally haven't done a lot of work with nanite, but they're conceptually similar. Nanite uses it's a simpler, more bare bones sort of approach that doesn't have as much of the infrastructure here, but they're conceptually similar items. I can't see. I think that, oh, there's one over there.
Is there like a demo app or something we can just unpack and play with?
There's not there are some examples within the Vertebra source. There's a whole bunch, I've put in a whole bunch of examples inside our specs, inside our tests. And so you can go to GitHub, right there, Engine Yard Vertebra. Actually, that should be Vertebra RB. Go to the Engine Yard area on GitHub and you'll find it. And there are examples there. We released a 0.4 last week, and we have a 0.4.1 that fixes a bunch of bugs that if it hasn't been pushed up while I've been here, it should be coming up there any time now.
What kind of security
model? Like, are you using PKI, like public key, or?
No, there's no public key. And on one of those facts back there, one of those URL links, oh, there goes my timer. So I guess I'm back there. You're the last one. But what Herald manages all of the security information, and right now it gets that information just via a configuration file, and then because eJabberD can encrypt all the communications via SSL everywhere, we rely on the eJabberD's security model as far as the JIDs and the passwords there to ensure that when an agent receives a request from somebody, it actually came from who eJabberD is saying it came from when it goes to Herald to ask for authentication. And since the timer went off, I guess I wrap. Thank you very much.